Good afternoon, ladies and gentlemen. Welcome to BRUKER Nanosurfaces webinar on More Than Just Roughness, an Introduction to Non-Destructive 3D Surface Texture Studies using 3D Optical Microscope. My name is Sue Ting and I would be hosting today's webinar. Before we commence, we would like to share that all attendees would be on listen-only mode. There is an opportunity to interact with us, and we encourage you to ask questions in the questions window. There will be a 15 minutes presentation followed by 10 minutes of Q&A, which our speaker will answer at the end of his presentation. If we are unable to respond to all your questions due to time limitation, we will respond to you through email. Without further ado, let me introduce our speaker for today, Dr. Yogesh Jeyaram. Dr. Yogesh Jeyaram serves as application scientist at BRUKER Nanosurfaces, responsible for application development and technical support of surface metrology instruments. His academic background was in solid-state physics and material science. He obtained his Ph.D. in UK Leuven, Belgium, working on linear and non-linear optical effects in metal nanostructures. Prior to joining BRUKER, Dr. Yogesh was a postdoctoral researcher in University of Toronto. He has published in over 15 peer-reviewed international journals. He also presented at many international conferences. We now invite Dr. Yogesh to share with us on More Than Just Roughness, an introduction to non-destructive 3D surface texture studies using 3D optical microscope. Dr. Yogesh, please.
Good morning, everyone, or good afternoon. So thank you, Sue, for the introduction. Today, we'll be talking about surface metrology tool using white light interferometry technique, and then we'll be seeing what it can do for your application. So the broad outline of the talk is going to be, we're going to talk about the basic principle behind the white light interferometry, and we're going to discuss some of the different modes that are there and when to use which one to suit the application. Then we're going to a little bit learn about what more can we do from the 3D measurement. So what, other than roughness, what else can it inform us? How can it improve our research goals? And then I'll also briefly touch upon some of the new technological developments that are taking place in this field. So let me first talk about where all it's being used at the moment. So the surface metrology, especially the white light interferometry technique, is being employed by many different industries at the moment, from automotive, from orthopedics, and also like contact lenses in medical device markets, or making drill bits and solar cells, or also in PCB semiconductor industries. Many different places where you need surface characterization. You need to understand the smoothness of the surface, how well the soldering is done, certain features, certain contours that we need to measure, then you can do it. So we have a saying, if you can't measure it, you cannot make it. So that means basically saying, if you cannot measure a parameter, you cannot control it or improve a certain parameter. So that's one of the key things that's driving behind this technology. So why use white light interferometry technique? So it's compared to the traditional surface profiler, it's a non-contact. It's fast, so you can get, for example, a 4 by 4 millimeter area in few seconds instead of traditional, few tens of minutes. It's accurate. The accuracy is in the range of nanometers. It's repeatable, so it's largely automated, so you don't have to worry. So it's very repeatable. And then you can measure topography, you can measure the waviness, you can measure the roughness, you can measure some special parameters like S parameters, all those things. So here, if you can follow my mouse pointer, so this is like a traditional microscope setup, the white light interferometry, but the objectives are interferometric objectives. So if you look at a normal microscope image, that would look like something like this, right? So it just looks like black and white camera. If you have a black and white camera, it looks like this. Whereas in interferometric, using our interferometric objective, you'll start seeing these interferometric lines. So we'll talk about them a little later. And once you measure them, you can get renderings, like 3D renderings like this, or you know, a little bigger areas. You know, it's like a 2D rendering, and you also see some kind of line profile there. We'll go through them one by one in the coming slides. So a little bit about the technology. So it's based on interference, I mentioned. So what is interference? A very brief introduction would be, so if you have a single source of light, and then you split them into two parts, and one of them goes through a slightly longer path length compared to the other, and when you recombine them, you get this kind of interference fringes. If you'd have gone in a rainy day in the parking lot, you will see this oil slick, and you see all these colors. And these are coming from the interference fringes, coming from the top and the bottom layer of the oil surface. So we use these interference fringes in white light interferometry like a contour map. So many of you would be familiar with the contour map. So it's going to look like this one, the bottom image. So you have all these lines. So each line represents a certain altitude, and you have certain numbering on them, saying what's the altitude number there. And the closer the lines are spaced, that means the steeper the elevation is. And then on the top, you see there is no lines. That means it's a very flat surface there. So what is missing in our interference images normally is this numbering, right? So you do not know, for example, the interference fringe here is coming from a concave or a convex shape. So we will talk about it later, how we can get this numbering using white light. So how it's implemented in our system is like, so you take a single source and you split them using a plane beam splitter, and then one half of the beam goes to your reference mirror, the other half goes to the sample, and then you recombine them back and you collect the light in your CCD. So ideally, if you have both your reference mirror and the sample exactly the same, then you have path difference 0. That's at the focus point. The path difference will be 0, and then what you see will just be a bright light in your CCD. But that's not the case. So you're going to always have roughnesses and the surfaces different from the reference mirror, and this creates the optical path difference, and this is what you measure. So that's why it's called the optical path difference, and all the files you save will be called the optical path difference file. And this is the main data. And this creates the interference, and from that we can calculate all the parameters that we're interested in. So little bit more about the fringes. So if you take let's say two plane wavefronts, right, two beams, say two wavefronts, and then one of them is tilted from the other, right? So then you have the tilt, and then you have this certain places where you have the difference between the plane one and the tilted one as lambda. That's the wavelength of the light you're using. Certain places you have 2 lambda, 3 lambda. So every integral multiple of this lambda, you get a bright fringe. It's like a bright fringe here. And you have the half integral, that's you get lambda by 2s, you get the dark fringe. So this is like a monochromatic light. And if you use a red light, you get something like this, right? Let's keep this in mind. So if you have these kind of bright dark fringes, when you have the small tilt, and then we talk a little bit more about them later on. So if you have a lens or something like this, like convex shape, then what happens here is we try to change the position of your objective, and we change that. By that we change the focus position, and thereby we see where we get the fringes also changes. So if you focus on the top position, you get the fringes like this, and whereas if you focus a little bit lower, somewhere here, you get some fringes like this. So, and then you move your objective basically, and then you collect the whole, you recreate the surface, right? So I talked about, so this is very similar to a normal microscope. The difference in this white light interferometry is basically the objective and then the algorithms that analyze your data, right? These are the two differences. So if there are 3 main types of interferometric objectives. The most commonly used ones are Michelson and Mirau. So Michelson is basically, many people are familiar with the Michelson interferometer. It has the same principle. and Mirau is a slightly a different take on that principle of interference. Right? So Michelson is basically saying my sample is here, and I have a beam splitter in front of my objective, and then one half goes to the reference mirror and the other goes to the sample, and then I collect them all through my objective, and I analyze it in my camera. So for example, here you have the reference mirror here, the beam splitter somewhere sitting inside the objective, and your sample is here, right? Whereas this technique works for low magnification because you have enough working distance space to put your beam splitter and other things. But when you go for higher magnification objectives, like more than 20x, then your working distance is very small. There you come up with a new design, and the design is the Mirau Interferometric objective. And here, instead of one beam splitter, you have basically two. So you have a beam plate here, and then another one with a mirror here. It's a very small mirror. Compared to the field of view, it's negligible, so it doesn't affect your measurements really. So you have this kind of techniques, and you can go up to 100x in this. There's another technique called linear interferometric objective, just for especially ultra-long working distance experiments. So for most applications, these two would be sufficient. That's good. So basically, if you use a Mirau objective now, so you basically have a little more detail here. So you have the source, and you split them here. Right, one goes to the reference mirror, the other goes to the sample, and then you collect them. Right. So and then the path difference created by the sample roughness and other things would create the interference fringes. Right. So the one advantage of relying on interference fringes instead of just the focal depth or things like that would be the resolution is very high. So the Z resolution is not limited by the objective. It's very high. It's about 3 nanometers. It's the Z resolution. So there are 3 major modes that are there in a white light interferometric technique. One of them is called the Phase Shifting Interferometry, or PSI. These technique can be used for ultra high resolution imaging, sub-nanometer Z resolution for very, very smooth surfaces like your silicon wafers or your mirrors, or very fine thin film coatings, those kind of applications. And then you have a vertical scanning interferometry. Here the resolution in the nanometer range to the millimeter. You can measure all kinds of roughnesses from nanometer range to millimeter. So it's kind of like an all-terrain vehicle, I like to think about it. Whereas the phase shifting interferometric technique would be something like a Formula 1 car, right? It's for very high speeds and very smooth tracks, works brilliantly, but whereas the all-terrain vehicle works on all tracks, right? But with a little bit higher noise floor. And then we have different techniques to measure thick film and thin film, thickness of the film, or the basically if you have a transparent film, we can measure how thick the film is. We have 2 different modes to measure thin films. That's like say 100 nanometers to 2 microns. Or if you have a really thick film, it's greater than 2 microns. You can use the thick film mode to measure it. Right. So let's talk a little bit about the phase shifting interferometry, or the PSI technique. So as the name implies, what you sense here is the phase change, right? So what you do is basically you have the light, and you just change the phase of the incident light, right? If you change the phase of the incident light, and then you still detect it, right? And then basically your fringes also will shift if I change the phase, right? I think you can see the image move. So basically, if I have a mirror, let's say, for example, and then I shift the phase slowly, 90, 180, 270, and 360. So then I can get this fringe shift. So basically, I collect all the intensity, and then I can calculate the phase. Right. And I can use this information to calculate how smooth or the roughness of the sample surface. Typically, we use a monochromatic light for this kind of application, and the resolution is very high. As I said, it's sub-nanometer resolution you can get through this technique. So here I show you an example. It's a very, very flat mirror. Similar ones are used, for example, in satellites where you have these mirrors there, or many different applications. So here the fringes, if I just look at the fringes, I would just say, oh, it's very smooth, there is no roughness, it's like the fringes are parallel to each other. But whereas in using phase interference technique, I can actually see the RT, right? There is some roughness involved, which is only a few nanometers, but I can see it using this technique. So you can get this AFM kind of resolution in Z very quickly and over a large area. Then the vertical scanning interferometry, this is like an all-round player, so you can do pretty much many different samples, all kinds of analysis using this technique. So if I mentioned, right, so you remember the previous slides where I have two tilted wavefronts and I created these interference fringes, and I said the distance between the two bright points would be a lambda, right? That's the wavelength of the light. So if I use blue light, for example, the distance from the 0 lambda to 1 lambda would be a lambda, and 1 lambda to 2 lambda is also another lambda, right, of the blue wavelength, so just about, let's say, 450 nanometers. Now if I use a green light as well along with it, now you see the green light also has a lambda difference, right, between the bright fringes, but the lambda is bigger than the blue light, so you see some shift, right? Now if I use the yellow light, then it's another shift, right? So basically in a white light, I have all these different colors, right, blue, green, yellow, and things like that. And I can use this shift that you see between the blue, green, and yellow as kind of like a numbering of your contour, right? So I can now tell which is a concave or a convex surface. So if you have just a black and white camera, then you just get a sum of all this intensity, which is going to be like this, which can still inform, right? Which can still inform me which is the 0 position and how the surface is going. If it's tilted above, only I would see from here, the center to this point. If it's tilted below, I would see this way, right? Okay, so then you can use this kind of information to see. So now to compare, right, if I use just a monochromatic light and then a white light, how the fringes would look. So if you had a color camera and if you have some surface like a grating and you tilt it a little bit compared to the reference mirror, you get some kind of fringes like this, right? So if you use a red light, you get fringes like this, and if you use a white light, you get all these colorful fringes. So if I just look at this monochromatic fringe, it's difficult to tell, okay, which is the top surface of the grating and which is the bottom surface of the grating, right? Because I have no reference. I do not know where is the center point or anything. Whereas if I look at the white light, the colorful image, I can clearly see, right, this is the brightest point and that's the 0 position. And whereas I can see another bright point right here. So then I can clearly see which is, okay, I can see this. Okay. Basically, by actually even counting the number of fringes, you can even tell how high the grating is. But you don't have to do this. All these are done. Algorithm will take care of you. But this is the principle that drives the algorithm to give more accurate results. So in general, if you have very rough surfaces, the white light interferometric technique is very accurate compared to PSI technique. PSI technique is limited up to lambda by 4 roughness. So if you use a green light, which is typically what we use, the wavelength is about, say, 560. So your roughness can measure up to 140 nanometers. You can safely measure. So here is a video of how the VSI technique works. So before I start the video, I explain a little bit about it. So you will observe this objective where the arrow mark points, the objective move. So this is a cartoon, and then on the right side you have this black and white image, and you will see the fringes appear on the top surface first and then on the bottom surface, right? That's a real actual CCD video of the sample. So you can see the fringe appearing on the top surface, and then as the objective moves, the focal position changes, and then it measures the bottom surface, right? So when you capture the image, you're looking basically at the best contrast of the fringes. That means whatever point is in focus, you measure the fringes at that point. That is when it's on the top, you see the top surface, that's the best contrast you get, and then when you move the objective down, you get the best contrast fringe on the bottom surface. And this information is collected by the computer and analyzed by our algorithm, and then you get the surface, right? So even though the optic image looks very smooth, you can see the rendering, you see all these kind of surface features, right? A lot of roughness. You can measure these kind of data, right? Typical surface, like for example, a metal surface which is machined or things like that, you would get a very rough surface, right? And then you cannot see this very nice fringes that I showed you before on a very smooth surface. So the fringes here typically looks like this, and I change, and I change the focus position from A to B, and you can see it's very difficult for a human to analyze it. That's why we need the algorithm to help us with these kind of processings. Okay, so to summarize, so it's a true 3D measurements. You get the surface area. You can measure all kinds of surface, rough surfaces, and you get good results. All kinds of reflective surface. So you can measure very black samples, like black polymers or tires or O-rings, and to very shiny surfaces. You still get very good results in these kind of techniques, and it's invariable of the objective you use, and there are no step height ambiguities, right? So you can measure from nanometer to millimeter range. So you can measure all kinds of surfaces and roughnesses. So when we measure, what do we normally measure? So every time you measure, you get three kinds of information. One is the form of the surface, and the second is the waviness of the surface, and then the third with the roughness of the surface, right? So here I use this mountain, which is near our factory in Arizona, and you see the form basically means is this rough outline, right? So for example, if I have a ball bearing, the form would be the radius of curvature of the ball bearing. So here in this case is this mountain as this form. And the waviness for visualization purpose, you can think of it like a big rocks on top of this mountain, right? There are these massive rocks on the mountain which are bigger than us, and this creates the waviness, right? So here, if you look closely in this picture, you see a lot of big rocks, right? You can climb on them. This creates the waviness, and the roughness you can think of it like is the small stones under your feet when you walk up the mountain, right? There are all kinds of small stones that you step on, like pebbles and small rocks, and these create the roughness of the surface. So every time you measure, you make a measurement using the white light interferometry technique with these three data, right? The form, waviness, and roughness. And by choosing appropriately the filter, you can get the relevant information. So for example, sometimes I'm interested in the form, right? I'm making a ball bearing, I'm interested whether the radius of curvature is as per my design wishes. Then I'm just interested in form, and I'm not interested in waviness and roughness. Whereas certain cases, I need the roughness data, right? So I need to prepare a surface before I coat it with a hard coating or a different polymer coating for application. So then I need to know the roughness so that I can estimate the adhesion properties will be good or not. So different applications require different parameters to be measured. Every time you measure all three, so you can actually get the data what you want. And all the three data is always stored, so you can always go back and ask different questions and get different parameters out of the software. So basically, to summarize now, all the things that I mentioned. So you have white light interferometry or the VSI technique, vertical scanning interferometry technique, and then you have the phase shifting interferometry, right? So the vertical resolution of the white light is 3 nanometers, and the PSI is in 0.1 nanometers, right? 1 angstrom. And then the roughness you can measure up to 10 millimeters in a BRUKER white light interferometry tool, from nanometer to 10 millimeter, so big range. Whereas in PSI technique, you're limited to lambda by 4. That's about 140 nanometer roughness. So if your RA is below 140 nanometers, you can use PSI technique. So the white light technique can measure rough samples, steep sample. PSI technique is mainly designed for polished material with very low height variations. The speed for white light interferometry can vary from 5 to 80 microns per second. That's how fast you can move your objective in the Z. whereas in PSI is a second or two, right? You can quickly change the phase of the incident light, so it's very fast. Okay, so BRUKER, these are some of the examples that we have done using our 3D microscope. So you have from sub-nanometer here, like a wafer, all the way up to a few millimeter level range, right? This is like a big step here. It's about 2 millimeter range. So you can measure all kinds of surfaces. And these are some surfaces of a cylinder, and you can see the honing angles. And you have some milling surfaces, and you have some pits, maybe due to corrosion or other reasons. And you have differently prepared surfaces, different roughnesses. One instrument can cover the whole range of it, right? So, so we talked a lot about getting this nice 3D images. Traditionally, people, when they talk about surface roughness, they would talk about a stylus profiler data, right, which is like a 2D. So you get X and Z or Y and Z, right? That's it. So then you measure RA, RQ, and all those things. So why do we need the SA? So first, let's understand what SA is. SA is like 3D data, a 3D equivalent of RA, right? So if you have a line profile, then you can calculate RA. If you have like a 3D image, you calculate SA, right? It's just basically a double integral of instead of a single integral when you do RA. These are all ASME standards. So you also have ASME standards for S parameters, like you have for R parameters. So why do we need SA? So here you have two different surfaces. One is like machine, and you can see the machining lines on my left side, the image on the left side. And on the right side image is just like a ball mill, right? It's just, it's a bead blasted surface. And you can see these two surfaces, if you measure just the RA, they will be identical. But anybody would have done any experiment would tell you that these surfaces will be completely different, in the experiment. Or, for example, if you're trying to make engine component, the machine surface will be completely different compared to the bead blasted surface, right? And that's why you need the SA parameters to tell you a little bit more about the surface than just the RA or RQ would give you. And that's why a lot of people are gravitating towards these kind of 3D aerial parameters. And that's why we need these techniques like the white light interferometry to give you this data that can be helpful when you're trying to develop your engine or other components. So here are some examples of differently milled surfaces. So these are you have different kinds of milling processes or finishing processes when you do engineering, and then you have these different surfaces that comes out of it, and you can clearly see that each one of them is very different. If I put some of them, they might give you same RA, but they would behave functionally very different. And that's why you need to do this kind of things. So we talked a little bit about SA. What other parameters are there which use this new 3D image? Quite a lot of them. So you have these amplitude parameters, basically SA, SQ, SZ, and things like that. So these are roughly analogous to your 2D parameters that most of you are familiar with, like RA, RQ, RZ, RKU, etc., etc. There are new parameters like these hybrid parameters, SDQ, and then you have the spatial parameters, and then you have also some functional parameters, right? Functional parameters can tell you about your bearing area. Can get the bearing curves out of it, and how the certain lubrication, what's my fluid retention ratio of the surface? Will it retain more fluid or less fluid compared to my original surface, right? So those kind of things are very useful when you're trying to develop a new engine component or a machining component. You want to know the lubrication, what kind of lubrication to use. So these kind of data can help you really a lot. And also there's a lot of evidence in the literature that these parameters actually correlate to the real life experiments. So here, if you see a triangle, that means there's a lot of evidence that measuring these parameters help them, and you can actually calculate or predict how a surface would function in real life by just measuring and controlling certain parameters. So I mentioned about these functional parameters like measuring the Abbott curves and measuring the fluid retention ratio, the lubrication behavior of surface. And you can see here it's all all triangles, right? So you see you can measure different kinds of functions of bearings or seals or friction, joint stiffness. There's a lot of evidence by measuring and controlling these parameters, you can get a lot more out of it. So a lot of ISO standards on this, a lot of research publications on this. I mentioned some here. You can find more if you do Google or do the web search on that. So let's move a little bit towards the different applications. So we talked a lot about this, the functional parameters, right? Here I talk about one, that's the SVI, or we call the fluid retention ratio. So here we have an engine block. An engine block inside the cylinder is honed, right? It has this kind of lines that are angled at a certain angle, and people play with it so that they want to keep adequate amount of lubricant in there so that it helps in the motion of your engine, but not too much that it impedes it, that it impedes the efficiency. So you can use these kind of parameters. So this curve, many of you might be familiar, is like an Abbott curve. So you can use this curve to calculate a lot of parameters, and one of them is the SVI parameter, and you can tell how good it is, right? So here we have similar surface. Now we do a lot more analysis. So now we have take a new cylinder bore, and you have take another bore that's used for 1,000 cycles or something like that, and you calculate and see, right? And you see all these parameters, the bearing index, and then the fluid retention ratio, those kind of things. And you see a new surface compared to a used surface, and you can see they are still okay, right? They're not so much difference. That means you can safely say that you can run up to that many cycles, right? Maybe 10,000 cycles, 10,000 hours or something like that. So you can safely use it, and so you can use these parameters to help you. Okay, great. So we have different tools. BRUKER has different tools, and one of our tools is what we call NP Flex. And using this tool, you can actually no need to cut open a cylinder block or an engine block to see inside of it, right? Before or after. So you can actually use the engine block as is, and we have this special objectives that can go inside, and they can actually map the surface. You can actually map the this whole cylinder, and you can stitch it as well, and you get the whole side wall of the engine. And you can clearly see here some hone angles. So continuing with our theme, so then you have wear, which is also one of the important parameters that needs to be controlled. So there are a lot of different techniques to do wear experiments. One of them may be using our reciprocating drive in our Tribolab tool, and you get this wear scar. Right? So you can measure the wear scar, and you can calculate all kinds of parameters from it. Traditionally, a lot of people use the waviness parameters and things like that to calculate how much volume they have lost from the surface, right, due to the wear. And now, with all the new tools, you don't need to go through a roundabout where you can directly calculate, for example, what's the volume lost, what's the surface area increase because of this wear marks. You can calculate, all kinds of parameters. What's the surface area of the wear, and where are the material pileups? You can calculate those kind of volumes there. Roughness increase, everything you can calculate quite easily. So here is an example of a O-ring, and it had some falls due to the operations conditions and things like that. And you can measure these kind of falls, and using certain techniques like the multi-region analysis, you can kind of calculate what's the volume or how deep is this scar, and things like that. So here you see, compared to the engine block, these are very black, so low reflecting samples. You can even with this, you can get a very good data. So the reflecting, even though we use the reflection as the main source of your signal, it doesn't affect right? You use a dark sample or a very bright sample like a mirror, you can still analyze the surface. So for another example where these kind of techniques is used is in the LED. So you have the LED, and these are or sits on a sapphire substrate. And this is the backside of the substrate, and you have all this porosity that we need to measure and control. And so you can use this. So normally in the old days, probably you just get an image like this, and you have to measure manually what's the length and how big the pores are. Now with using the multi-region techniques, you can quickly identify, what's the different pores are, how big they are, what's the volume there, everything, right? This is automated. So no human error or anything, and you can calculate really huge amount of data quickly. Right? Probably take you less than a few seconds, right? Maybe 5-10 seconds, something like that. So this is a definite advantage for the technique like white light interferometry. So it's repeatable. So if you're measuring for samples like the LED industry, you are measuring a large area samples. So you need it to be repeatable. Some of the surfaces can be low reflecting intentionally, so you need to be able to measure that. And you should be able to do this real-time analysis, right? And you can do all that and very quickly as well. So here, another example would be in the optics industry when you have the super polished glass substrates, right? For many different applications. If you're developing an X-ray optics, or you're developing new UV lenses, or you're developing optics for lithography, you need to be able to have your lens surface at a certain tolerance, right, which are very high. So it's sub-nanometer tolerances there. So you need to be able to measure it and quickly, right? So if I have to take every time a lens and measure it in AFM or complex signal, then it's a little slow. So you need a very fast technique with this kind of very high Z accuracies to be able to do that. And that's where white light interferometry techniques can come. So you can get a very large field of view. So here, for example, you can see the field of view is about 1 by 1 millimeter, which is fairly large. So on the resolution, you see the RVA is 0.1 nanometer, right? We use this measure with the PSI technique. So if you use, for example, techniques like confocal, then you have to choose a very high objective, very high magnification objective to get this kind of Z resolutions, but then you sacrifice on the field of view, right? So you're only able to measure a very small field of view, which is then limiting again because you want to be able to analyze a very large area very quickly. And so we can use our technique, so then you can measure a very large area very quickly with very high resolution. So as I mentioned before, so the interferometric technique are not limited by the magnification of your objective, right? So if you use a 5x objective or 100x objective, I can still get a Z resolution which is sub-nanometer using PSI technique. So some examples from the polymer. So you have different kinds of polymer, and then you are trying to see how these polymer additions are to a certain different surfaces because you coat them for improving certain properties. For example, many of you are familiar with Teflon coatings to make it hydrophobic, right? So you have different properties that polymers are largely used. So some of the customers who use it, I mentioned also on the top, so like Dupont, 3M, they develop a lot of polymers and they want to see how these polymer things are. And surface property also influence some of these functional properties, right? So surface roughness will influence your adhesion or the longevity, so how long does your film last. So those things we need to control. Then we can use the white light interferometry technique to measure the waviness, for example, in this mylar film to see how good the adhesion, how good the adhesion can be, right? We can expect before actually testing, and we can see how control the waviness so that we can get a certain adhesion behavior from these films. And for example, it's in the blade manufacturing, or Gillette, or some sheet metal manufacturers like Mittal or Alcan. Surface roughness is also important. In some sheet metal manufacturing process, you have two different sheet metals with roughnesses, and you kind of like cold roll them or hot roll them, and then you bond them, two different metals or two different alloys, And also, like, for example, in shaving blades, the sharpness of the blades are very important, so you need to measure the roughness and those kind of things. And also sometimes we engrave them, so you kind of have this burrs, so you have this elevated features, right? And we need to be able to measure with how big the burrs are, how smooth the sheet metals are, how smooth my blades are, and then we can tell a little bit about how it's going to actually function, right? How good the rolling process is going to turn out to be. So we need to control this so that we can actually control the final product. All right. And some examples from the semiconductor industry. So semiconductor industry, the White Light Interferometry tool is used almost at every step. So from wafer manufacturers all the way to the packaging side. And even when you do the PCBs to check that the solderings are done correctly. So for example, if you take your mobile phone, almost every part of the mobile phone has been processed by a White Light Interferometric tool, and many of them are BRUKER tools as well. Right? So then you can do this kind of analysis. So here you have the bare wafer analysis to measure the surface roughness is okay. See the etching profiles, you can measure them, how good the etching is turned out to be. And for example, you have a lot of bumps here, some silicon bumps. And then you have the probe marks. So for example, when you test, after your IC is packaged, you test your wafers, whether they're doing okay. And then you have this metal probes, which sometimes land quite hard on the surface, and you leaves a mark, and you can measure how bad the mark is, whether it's going to affect the performance. Or your wire bonding imprints, or your lead frame roughnesses, and then when you do this laser burn marks on the packaging of the chip. Right? So it's used in almost every part of the process. So here are some examples from precision machining industry. So you have polishing pads. So these are these diamond crystals, and you use these things to polish your sapphire substrate. Right? So now a lot of mobile manufacturers are talking about using a sapphire glass to cover your phone. And there you need to polish the sapphire to a certain tolerances, and you need these diamond crystals, and then you monitor how long your polishing pad lasts, right? Because sapphire is also a very hard material, and these pads needs to last quite long, otherwise they're too expensive. So you can control not only the end result of that, you can also control your abrasives, right? How long they last, how good they are they still usable? These kind of questions you can answer them, right? And here is the counter surface, right? The glass, so which is what normally we use abrasives to polish. You can see some scratch marks, so some scratch testings are done. For Gorilla Gas, those kind of things. So you need to we say it's a scratch resistant, so we have to test it and then we prove it. We don't leave a visible scar or how deep the scar is or how visible the scar is. Those things can be measured and controlled after a scratch test or before the scratch test, right? Some examples. So this is, I think, is a Malaysian coin. So if you have a rupee, or I'm from India, so we have rupees here, and your coins, and US cents. Every country has a coin, and you have all these nice features there, right? These are all stamped using a mold, and you need to not control how good the reliefs are, because you need to be these reliefs are quite complex to prevent counterfeits. You need to make sure that the reliefs are well developed, and also the mold is not broken. Right? So if the relief is broken, not good, so you need to see whether the mold is bad or the mold is worn. So we need to control those kind of things. So people use our tools to do this kind of controls. Now, touching a little bit upon the medical industry. So this is the orthopedic industry. So if you have old relatives who have hip implants, so they have this two surfaces where you replace the hip with this metal things. It's like titanium alloys, and you have different kinds of roughnesses. So you need a certain roughness. It can't be too smooth, so then you don't have any muscle or anything that grows on them, right? You need to enable some growth of certain biomolecules on top so that it's taken well by the body, and it can't be too rough that then it's start damaging your other parts of the body, right? Or the counter surface of your hip implant. So we can see here different steps of the process, how the final polish or final finish is obtained, and you can measure and control. So for example, here you start with the raw casted, and you can see clearly the molding lines or the casting lines, and you finish it, the first step, and then you smoothen it, you kind of, there's no more those lines, and then you kind of polish it, and you see it now start seeing the polishing lines, and you try and repolish it again, and then now it's quite smooth. Right? And you can also see it by eye, but now you can control it very to the nanometer level quite precisely. This is the counter surface of your hip implant, right? So that one would be, so this would be the socket in which that implant sits, right? So this also needs to have a certain amount of roughnesses, and certain the smoothness also needs to be controlled. The contour also needs to be controlled, so it has to have a certain curvature so that the counter surface can sit quite well and not too loose or not too tight, right? So that it enables movement. So you can see here different steps or different samples. You measure it at the different points. So pole is measured at the top of the surface, and then we measure at different points, like Q1, Q2, Q4, and then you can see how the RD and RQ, that's what we control here, is changing from point to point, right? So here I actually even show the counter surface here. So here you can similarly you can measure the pole roughness and then the different point of roughnesses, and you can control them, and you can see, well, the pole is slightly out of tolerance, right? Much rougher than compared to the other points. So probably they need to optimize the processing to get the roughness of also the pole down, right? So our example here is a dental implant. So if you have root canal done and you have new tooth, and you can measure these kind of threads, so how thick the threads are, so you can control them, and you can also automate them. So using our tool, you can also automate. So if you have many threads, you don't need to manually go there. You can make your system automatically go, right? So for example, you have for example 10 steps, right? 10 points. Automatically goes there and measures these 10 points, and see it measures here RE and RQ automatically at these 10 different points. Right? So you can automate it as well. So if you have a very large sample, you can do that. Some glass components, for example, in the projectors or things like that. So you have these glass lenses, big ones, and you can measure. So these are quite big, right? So it's about 40 millimeter, very big lenses, and you can still see some fine features. You can see, actually, if you look closely, you can also see the molding lines, and you can also see some pits and things that are some faults that are there in the glass. So these are okay, but there are certain tolerances that needs to be controlled, and we can measure that. So here are some laser engraving. So you put your brand name there, if you mark it, and then you create certain amount of burrs, and you have certain molding the marking depths. You can measure that quite accurately and see. So these are also there in contact lenses, and if these burrs are too high, right, or too sharp, then it's not very comfortable feeling for the wearer. So you need to have them below a certain height or certain roughnesses, so that it's acceptable to the user's eye. So here, more applications from the contact lens. So one of the things that they need to measure is the lens's curvature. So we need to make sure the shape of it. So here you have different polishes, and see after a certain polishing that the curvature shoots up, right? Which is not good. So then they need to change certain things in the polish, so that make sure that the curvature doesn't jump or reduce or increase, right? So to maintain certain roughness. And also, so if you have bifocal things or lenses, bifocal lenses, so you need to have these kind of complex Fresnel lenses. So you have these steps, and then you can measure them. You can see clearly here, and you can also measure the distance between each step, and you can measure the height of these steps. All these things can be measured, and they use it to control the processing, so that the end result is as designed. Right. And here some from the precision engineering again. So here is like a watch gear. So if you have a high-tech watch like a Rolex or things, there are a lot of these mechanical components, and teeth needs to be of certain dimensions, and we need to measure it. And when you precision machine it, there's always some deviation from the design part, right? So you expect it to be 1 micron, so it's 1 micron and 0.5, 1.05 micron. So we need to know how much the deviation is and whether it's acceptable, things like that. So we can measure those things. We can measure the diameter of the different rings, the angle between the arms, the gear thickness, the width of the wheels, everything we can measure them quite easily. So I talked initially when I talked about semiconductors, so you have this probe marks, right? And these probes are actually these ones. So you actually measure also the probes, the shaft surface, so that it's a spring inside, so that the loading force when it touches the substrate is not too high. And you need to also control the roughness of this so that it doesn't scratch or aberrate your silicon wafers. So you can measure that as well, right? We do measure these things for some of our customers. And if you have oil pipeline or a gas pipeline, so you have these kind of what you call coupons, right? So instead of if you want to check whether the corrosion happens in the pipe, so you don't take out the whole pipe, so you have these coupons inside at certain places. So you take out these coupons. So these coupons are something like this kind of cylinder that are sitting inside the pipeline, and then using an MP flex system, you can actually measure the whole surface, and then you can stitch them, right? So then you can open it up, so then you can see all these corrosion pits that happens, and then you can measure the volume of the corrosion, how much the surface area increase, and you can judge whether the pipe is still functional or it needs to be replaced, right? Those kind of things we can calculate on the live system. So this is not research tools anymore. These are more of a control process, right? So if it becomes really bad, then your pipe looks like this, then it's not really functional anymore. Too many losses or leaks, things like that. So now there are new software that we released. It's called Vision 64 Map. So this improves our existing software, so it enables a better visualization, rendering techniques that comes with it, and also language support. So now you can get in 11 languages, the user interface, and you can use the software as a standalone one, and you can get all kinds of different standards, right? Not only ISO or ASME. If you're Japanese, you can get JS standard. If you're using the European standard, I think DIN for Germany, you can get all these kinds of standards as well. And you can get report more. So here, for example, I show an armature and some outside part of it. You have this different language support. You can get reports in all these different languages. Sometimes your customers are German or somebody, so you can use the German reporting and use their standard DIN standard. Or you can find the equivalent ISO standard, right? So ISO standard is 25178, and then you can find the equivalent DIN standard or JS standard, and you can also calculate it, whichever the standard you need. And so, for example, then you have all this new analysis that's possible now. So, for example, when you precision machine, I mentioned, so you have a surface, and the surface is not exactly what you want, but then there are deviations. Sometimes the deviation is positive, sometimes it's negative. So you can now have a surface, and then you fit, for example, a radius of curvature here, and you can see how it's deviating from this mean radius of curvature, right? Certain places deviating inside, certain places outside. So those things can be there. And you can set tolerances, right? And then if it's okay, it's below tolerance, then you get a green coloring, or if it's above tolerance, then you get a red coloring. So you can now do all these kind of different renderings, different analysis are now possible with our new software, right? So then basically we are coming towards the end. So this is the product line. So you have different products that we have for different application needs. So here you have the GTK, that's for lab use or some basic use, and then you have bigger systems like GTX and NP-Flex for big components like engine blocks and automated systems as well. So these are some basic overview about our system. I hope I covered some things we can do other than roughness measurement, just roughness measurement using a white light interferometry technique. We went through some of the strengths of this technique and some of what information it can give and where it's applied in different applications. Right? So if you have any questions now, you can feel free to ask or type. So here I have a question. How about how to measure drilled holes of a curvature instead of a flat surface? So I understand that you want to measure on the inside surface of the drilled hole, right? So that's basically like measuring inside. Yeah. Okay. So that's like measuring inside the engine block. So let me just pull up the slide if we can show you how to do that. So here is an example. So here you're measuring inside the engine bore, right? You don't need the flat surface. It's not flat anymore. So you're measuring the objective. Actually, you can see in the middle picture, you can see a light dot. So basically, the light comes from the objective and is reflected by the mirror onto the surface. So you don't need to cut open. It doesn't need to be flat. You can measure inside the bore. But then here the limitations are based on how big your holes are and things like that. We can talk a little bit more details about it. If you have, you can write us an email. We can discuss more in detail about your application, whether it's feasible for your holes. Okay. So let me put back the email ID so that you guys can note. Let's see. Okay. There you go. So you can write us an email on this address and we can get in touch with you. So also similarly, I have another questions of measuring inside a glass tubes. Say the diameter is about 0.3 millimeters. Okay. Yeah, I think it depends on how deep the pores you want to measure. If it's near the surface, we can try and do something because the hole seems a little small. Yeah, we can look into it in more detail. I think we can definitely measure inside certain bores. And as I said, here how deep you can want to measure in the bore is inversely correlated with the thickness of your tube, right? How you should be able to take in a long objective, then you can measure inside easily. If your diameter is bigger, if your diameter is smaller, the distance you can measure is rather short. So yeah, we can measure those kind of things. What's the biggest lens we can measure? So the GTK, that's one of the basic model. The state size is about 150 by 150 millimeter. So that's the only thing that's limiting you. So if you use the smallest objective, the field of view is about 4 by 4 millimeters. All right. And then you basically do a stitching. So you measure many of these and then you stitch it so that it gives this uniform view. Some of the lenses I showed you as being gone through this process, but you cannot see the stitching at all. So it's done very well. So if you take a bigger system like NP-Flex, the only limiting thing is the state size. So you can measure really big sample. I think 150 millimeter by the smallest system, and it can go up. Yeah. So did I miss any questions? Can form error be detected? How much it deviates from theory? Yes, we can measure that. So for example, here is a form of a surface or structure, and there's some deviations, and you see the green deviations are deviations within the tolerance, and the red deviations are deviations above tolerance. So there are some form deviations, and you can measure them where they deviate locally, not just global deviation, but also local deviations of the form you can measure. So Okay. I think if you have any other questions? Okay. I don't think so. We have more questions, but if you have, what's the max depth can we measure? Well, it depends. So I don't understand the question correctly. So is it the depth of the bore that you're asking about, or is it what's the deepest bit I can measure? So the deepest bit I can measure is about 10 millimeters, right? That's the Z range I have. So any roughnesses that's in the range of 10 millimeters I can measure. If you're talking about inside a bore, using certain special objectives, we can measure bore depth. You know, it's a 12-inch, so you can measure inside there. You can measure things like that. So yeah, so depending upon the objectives you choose, it can vary. For example, the bore depth, but the Z travel is more or less constant, about 10 millimeter. So then you can measure roughnesses in the order of maximum 10 millimeter. Okay. Okay. Seems we don't have any more questions.
Okay.
Okay. Now I'll hand it over to Sue.
Okay. Thank you very much, Dr. Yogesh Jeyaram. Ladies and gentlemen, that concludes our webinar for today. We hope you have found it informative and helpful. If there are further questions after this webinar, please email us at bns.asia@bruker.com. Before you leave the webinar, we would appreciate it if you could fill the short survey to help us understand and serve your needs better. Thank you very much and have a good day ahead.